Chemistry time. We're talking today about I'm going to make it big, atom. The atom. The atom bomb, the atom bomb. You remember that one? That song? From, I would assume, 1950 something, but also from Fallout 4. We are not talking about the atom bomb. We are talking about the atom in general, and as you might know, that does relate to the atom bomb. Why would we call that the atom bomb? Does anyone know?
Because it's all filled with atoms.
Yeah, and guess what? All bombs are made out of atoms, as everything else is. Like I could call my bracelet here the atom bracelet because it is made out of atoms. Why would we specify that in the atom bomb? What was special about that?
It can split.
Yeah. The idea being that the forces that hold the atom together are cleft, they're separated, and therefore the energy is released, and that is an enormous amount of energy for a given amount of mass, much more than a chemical reaction bomb such as TNT. Anyway, atom is a word from the Greek. What does the prefix a mean in Greek? Does anyone remember? Like asexual or abiotic? That a means no.
Double.
You're closer. No. Asexual meaning without. So a meaning without or no, etc. Asexual reproduction is that kind of reproduction without sexual intercourse. Like, for instance, a hermaphroditic worm might engage in. They just separate, and then there's two, and that would be an example of cloning, which is asexual reproduction. An abiotic factor of the environment is a factor of the environment which is not alive, which is without bios, life. Abiotic meaning without life. Tomos is from the Greek for, well, it has the same root word as tomography, as in computerized tomography, a CT scan, and it actually means to cut. So tomos, without cutting, meaning that this little thing, the atom, is uncuttable, basically. That's a colloquial way we could say this. Uncuttable, indivisible, one nation, under God. What, Cyrus? Nope. I got loads of them, actually. Lily, get him a pencil. Unlike a pencil that Cyrus will be given, which is cuttable, you can sharpen a pencil, the idea of the atom is that it was uncuttable. And it isn't really, as we just talked about with the atom bomb. The whole point of the atom bomb was that atom could be cleft, and the energy holding the atom together would be released as an explosion. Like the atomic bomb, yeah. So we know, so is this true? Is an atom actually uncuttable? No. Not really, but we still call it that because we were in the habit of calling it. And actually the idea for the atom came from a man called Democritus.
I think you mean Atomocritus.
I don't. I mean Democritus. And he lived, my book tells me, this is one of the many cases where I like to have my book out because it has numbers from 460 to 370 BCE, before Common Era. And so this is before, you might even say before the time of Christ, before the modern age. Certainly it's about 500 years before the birth of Christ, so that tells you how long it was, about 2,500 years ago. And his job, his role in society, in so much as it was anything, was he was a philosopher, not a scientist. Natural philosophy, science as we know it, didn't really exist back then. 460 to 370 BC, and this is when he lived. No, he's no longer alive. You'll be happy to find out. No, I think he was only like, wait, let's think about math.
He would have been
406 minutes.
We're going to have to cut this part of the video. Yeah. He would have been. That's pretty old. That boy is old as heck for an ancient Greek boy. When literally his food was only bread and fish and olive oil and wine, and probably the only thing he could drink was wine. Like, this guy, almost certainly a wino. Like, his liver was purple when he died, I guarantee. And he lived to be 90.
You have
What? Lily? What kind of shade are you throwing at me? First of all, I am not a wino. I think it's been, literally, Lily, I don't think I have had an actual even drop of wine since Christmas 3 years ago. So you cannot, right? You can call me a lot of things. You cannot call me a wino. I am not that.
Every time you drink, it's like, oh, this turkey real dry.
Yeah, that is so true. That is so true. Anyway, in so much as his job was, anyway, his role in society was a philosopher, as I was saying, science as we think about it today, the idea, Taylor, you have to, yeah, I did, I don't know.
I'm actually mad now. That makes me wonder.
Hold on, I have to pause this. What happened just now is that Taylor took a drink of his tea, and then I watched him do this, and it just came out onto his table. I don't know. Okay. Well, that didn't pause. I guess that's just going to be part of the video. Anyway, listen, please. We're all losing a little bit of touch here. Science as we think of it today, the act of investigating the world and coming to conclusions based on evidence, didn't really exist. What takes the place of science in society today, back then, was really a conglomeration of divine mythology and direct observation. Things like Democritus, he himself even may admit, like, the tree is green. And then he might go on to say, because Zeus probably kissed it. That's a cute way of saying it, Kendall. I'm glad you said it, because I was going to say something much more inappropriate. Zeus probably kissed a naiad. Zeus seduced a dryad here, and so now all the trees are green. I mean, that would have been science. So he was a philosopher, and basically his contribution to what we're talking about today is that he thought, in his wine-soaked brain, I can cut this, I don't know, cheese or meat or bread or whatever. I can cut this in half, and I can cut that half in half. I can cut that half in half, and that in half, and that in half. And eventually he thought, this is just a thought, he didn't actually do this, but eventually he thought, there must be a part where it would get so small that I can no longer cut it. Like, even if I had the sharpest knife imaginable, there must be a particle so small I can't cut it. And this was all in his thoughts, and so he named that thing the atom. Right? He, as a philosophical experiment, he devised, hypothetically, a piece of matter so small that it couldn't be cut, and that he called the atom.
Oh, and that's why it's
Atomos, yeah, it couldn't be cut. I need to get rid of this gum. And then a man called Aristotle came along. We're going to put him in a separate category over here. Aristotle came along and said, let me tell you, Aristotle lived from 384 to 322 BCE. And he came along and said, your boy Democritus is wrong. That's not how matter works. Matter is actually made of the avatar. We got fire, we got water, we got earth. I'm trying to draw the earth rune. And we got wind. And that's it. That's what all matter is made out of. Is he wrong? I mean, we ourselves as philosophers might say, you know, if we remove ourselves from the material, where we know this isn't the whole truth, but maybe, but this is science. This is serious. We're trying to learn about what the world is actually materially, empirically made of. And so we say, now, and actually this, surprisingly, this people held to be just basically the facts of life for about 200 years, until about the 17th century CE, about the 17th century CE, which is the 1600s, what we sometimes call the Age of Enlightenment. People like Leonardo da Vinci and Galileo Galilei and even Isaac Newton said, well, this is not it. And actually, one man particularly, he stood on the shoulders of giants, as we all do, but Antoine Lavoisier said, matter in its component parts is more like what we now call the periodic table of the elements, and less like these ideas of fire, water, earth, and air. Yeah, and yeah, I don't know. So no, like 62, I think.
Which means he was wrong. He didn't live as long as Democritus.
No, that's not how we work. So this idea we know I'm no longer in my life willing to say this is wrong, but I am willing to say this is unscientific. This is not the way we as scientists generally today view the world. Does fire exist? Yes. Does water exist? Yes. Does earth exist? Yes. Does air exist? Of course they do. These things all exist, but they're not the fundamental components of matter in a material, scientific, empirical sense. These are even, I will say this one more thing before we move on back to real science. In someone like my son, a 3-year-old, in the mind of him, these things are probably realer and truer than the elements are, because these are things you can actually interact with. Maybe air, not so much. But water is more important to us as a concept than rhenium, because we don't interact with rhenium very much. So, as a zeitgeist, as a cultural thing, this is important, but it's not materially, physically the way the world works. But this isn't really either, right? This is not, we know that an atom isn't just the thing that can't be cut. And so get out of here, Greeks.
Wait, what's that thing say? What's that thing say?
It says, I'm on page 102, come find me. Just look it up on page 102.
Oxygen?
Um,
Water. Earth.
Then,
Fire.
then, Dalton, who lived from 1766
No, he's going into
to 1844.
Wait, this man made
No. John Dalton, at some point between these 2 years, which I will tell you, a school teacher, like some of us are. Don't say, why do you both say, what the crap? Well, I'm standing right here in 1803 with just 31 years left of his life. You know, that's how we usually measure things. He had the idea of that he could see experimentally, this is scientifically, what we would now call scientifically, using the principles of natural philosophy and science, he could scientifically show that the combinations, when elements combine, when what were then understood to be elements, even like Antoine Lavoisier had already happened by now, and so we had something like, it wasn't the periodic table as we know it today, but there were a list of basic elements. Things on there like oxygen was on there, iron was on there, gold was on there. Several of the elements that we now have and we know are chemical elements were on there. And he realized that scientifically, elements combine in fixed ratio. Something we talked about in the last chapter too, remember? The H2O is not just about that it's made of hydrogen and oxygen. It's about that it's made of 2 hydrogens and 1 oxygen. The ratio is important. The classic example being that is that the same as that? Are these 2 things the same? No, this one's hydrogen peroxide, a poison, and we don't want to drink it because it's not good for us. But this one, the opposite. If we don't drink it, it's not good for us. So we know it's about the ratio, and he found that out, that the ratios are important. And from that, he deduced that these things there must be an individual particle, which he renamed the atom. Now featuring new and improved atom, now featuring science to back it up. So he took the name from Democritus. What then was Democritus' actual contribution to science? Yeah, he named it. He didn't discover the atom. He didn't scientifically demonstrate the atom. He didn't show evidence even of the atom. He just named atomos. And then Dalton found actual evidence that there is a more or less indivisible part of matter, a part of matter that is fundamental to chemical reactions, which he renamed the atom. When I say renamed, I'm using it in the opposite way we normally mean it. I mean, he found a thing and he used an old name for it and not put a new name on an old thing. Yes?
How did one dude think, I'm going to mix this and this, and then mix it with this and this, and make chemical reaction?
Yeah.
Like, what idiot.
Yeah. Yeah, you're probably like your great-great-great-great-great-great-great-great-great-grandma sitting there rubbing some sticks together was like, oh, this is a fire. And that is a chemical reaction, right? It's not like when you do a chemical reaction, the word chemical reaction is stamped on your forehead or on the forehead of the chemical reaction. It's just something that is part of life. To answer your question more specifically, for things like blowing stuff up, like the discovery of gunpowder, that probably was a surprise. And they're like, wow, when I mix these things together, kablooey, and now my house burnt down, and I'm going to sell this to the king.
Together, like, what were they doing?
Bored all the time. They didn't have TikTok. Everyone was always A, drunk, or B, bored, or 3, asleep. Yeah. Or D, dead. Thanks, Gabe. Okay, so from Dalton's idea, we get the new idea. Once he had realized that atoms constitute as fundamental, almost like building blocks, we now have this was then Dalton's, we could say maybe, it was kind of like a model. Remember that a model is something that shows the truths about a concept, but not exhaustively. It doesn't say everything about it. We now know that atoms are actually made out of different component pieces, right? At the time of Dalton's model, model, these were more like, kind of like the lab that you guys did with the clay. In Dalton's mind, the atoms were really like totally indivisible, balls, not made of clay obviously, but that combined in certain fixed ratios, and that was what they were, and that made up everything. Later, a man called William Crookes, Sir William Crookes even, discovered that part of the atom, Sir William Crookes, discovered the electron. He discovered that the atom, which Dalton had said was indivisible, and in fact named atomos because he thought it was indivisible, found that a piece of the atom could be broken off in the cathode ray experiment, and that was shown to have a negative charge, and so some part of the atom must have a negative charge. Some part must have a negative charge. Oops, not a parenthesis. And he found this out because he had a positively charged and a negatively charged plate on either side of his cathode ray, and the cathode ray itself was attracted to the positive end, and so that tells him that the cathode ray was charged negatively. And from this, Thomson, from this experiment that Crookes ran, J.J. Thomson, not your mom, but J.J. Thomson, a different J.J. Oh. Her name isn't just J.J. Anyway, J.J. Thomson trying to find the year here in my text, I'm sorry. In 1897, we're getting to be in pretty recent history now. I mean, like this is not yesterday, but it's not that long ago. Oh, and by the way, Crookes' experiment was, also 1897. So J.J. Thomson comes up with this idea of what he called the plum pudding model. Plum pudding model. Hey, do you know what plum pudding is? No, of course you don't. You're not English kids starving to death from 1897. You're Americans, and so you know what chocolate chip cookie is. Do you know what chocolate chip cookie is? So we might rename this today chocolate chip cookie model, where in his model it was plums inside of a plum pudding, but for us as real Americans who do things right, it's chocolate chip cookies. Yeah, we don't want no fruit or no pudding. We want chocolate in our chocolate chips. And his idea of the plum pudding model was that I always forget which one it is. That the matrix of it, the cookie or the pudding, has a positive charge, and then these individual little inclusions, which could either be chocolate chips or plums, depending on how free you are in the world, are negative charges. That's called the plum pudding model. We still call it the plum pudding model. I very seldomly hear it called the Thomson model, though you could probably call it that too. So his idea now, he took the evidence of the experiment, which was the atom has parts, and one of those parts is a negative charge, and he made a new model. Why would he include this positive charge? If the experiment only showed a negative charge, why would he make part of it be a positive charge, do you think? No. You're on the right track, I think, though. It has to be an equilibrium. If there was a negative charge at any point, we know the atom itself is neutral because it doesn't just have a charge. So there must be a positive charge in there somewhere else too to balance it out. And then a new experiment. I'm going to erase Dalton's over here. A new experiment, which Gabe and his partner know all about. 1911 lab partner. 1911. Ernest Rutherford. The dude from Westco. No. Ernest Rutherford. Ernest Rutherford came up with an experiment which was called the gold foil. Nice experiment. And what he had was basically a ray gun that shoots alpha particles. I'm going to write the Greek letter alpha all over the place. That one's a little bit crazy. It shoots alpha particles, and he had a detector that detects alpha particles, and he had a loop of gold foil. Now check it out. The alpha particle has what charge? Do you remember this from physical science?
Positive.
Great job, Taylor. That was not a guess. He just knows it. The alpha particle has a positive charge, and so if Thomson's model, if the plum pudding, if the chocolate chip model is right, and these all have a positive charge, and this is made of basically a lattice of positive charged cookies all stuck together with no space between them, right? This is just a stack of Subway cookies completely filled in with mostly positive charge. What would we expect to happen? no, that's not the kind of answer I'm looking for. If we shot out of this ray gun positive charges, and this whole thing is positively charged, what would we expect to detect at this detector?
Negative charges.
Let's try one more time.
Positive.
Yeah, none. We would expect to see nothing, because this positively charged everything in here would bounce back all these positive charges. And so we'd expect to see nothing here. But instead, what we see is almost all of them. I'm going to make an extravagant claim and say roughly 99% of the alpha particles emitted were detected over here. So what gives, says Ernest Rutherford in 1911. What gives? What gives? Well, what's the explanation for this? And from this we get a new model called the Rutherford model. What gives? What must be happening here? Is this mostly positive charged lumps? That's what we thought, but it obviously isn't. What must it actually be? If 99% of them are just getting through, it must mostly be what? Try again.
Neutral.
Lily's going to answer the question. Empty. It must mostly be empty. So instead of a big old pile of Subway cookies, it actually is like in the shape of this. It's faintly just like barely anything in there. We know now, and Rutherford was right about this, the atom is mostly empty. By volume, it is mostly just space. So a new model has to be developed. Is this one still going to work? Is this model still going to work, the plum pudding model? No, because that fills space. So Rutherford's model is what is on Jimmy Neutron. So he thought it must be the positive charge in here surrounded by orbits of negatively charged electrons. And this is where the NPPD logo comes from. This is where a Jimmy Neutron thing comes from. This is what people still think of when they say the word atom. Like if I was going to have ninth graders tomorrow draw atom, I don't even want to talk about that. If you bring that up in this classroom again, you will be banished. But these things, get out, Cyrus. So these orbits that Rutherford called them are surrounding what is mostly empty space. So there's a more or less solid nucleus that is positively charged. He called this the nucleus. We still call it that. Surrounded by more or less free to move around electrons, and in space filled largely with emptiness, the void.
They say that in Big Bang Theory.
That's cute.
Why don't you like this?
Why do you think that the neutron was the last one discovered?
It's the littlest.
Because
No.
it's neutral.
Because it's neutral. Right, so we can't detect it. The electron was probably the first one discovered because it's freer to move around, and it has a charge, which we can detect a charge fairly easily. This one was then discovered, the nucleus being positively charged was discovered when we found out it was mostly empty space, which includes protons. And now today, we largely use two models of the atom. We sometimes use the Bohr model. It was discovered by Niels Bohr that electrons actually inhabit, kind of using that word loosely, but they exist in orbitals. So the nucleus is at the center, but then there are these concentric orbitals. The Bohr model. Let me just tell you from the timeline. Great question. 1913. There are these concentric rings of electron energy levels surrounding a nucleus, but that it's still mostly empty space. That's the Bohr model. And we still do use that one. We use that one quite often because it's very convenient to show the energy levels of electrons.
What does the bottom say?
That's what they use for their lab. Energy levels. I wrote it kind of sloppily, I'm sorry.
And doesn't that also help us like model valence electrons?
Yeah, this is what we use to model valence electrons. Exactly right. Thank you, Gabe. And then it wasn't until 1932 that James Chadwick discovered the neutron. So the neutron was the last one discovered, probably as you said, because it's neutrally charged, it's harder to detect. But he discovered the neutron, and we found that exists in the nucleus at all. That exists in the nucleus also. And so then we come along with what we now use. I'm going to just put modern here. We use the electron cloud model, sometimes called the electron probability.
James, what now?
Chadwick. An electron probability cloud. And we use this one because we know the electrons, unlike in the Bohr model, are not spinning in circles like planets around the sun. They're happening to exist at one point in time somewhere around in some area around the nucleus and then stop existing there and start existing somewhere else. They basically teleport. And that's the electron probability cloud model. So we still have a positively charged nucleus, which now also includes also includes neutrons. And then we have this area, this kind of hazy area around it, like a cloud, where electrons may exist or are likely to exist. They're more likely to exist closer, and then they stop existing there and exist somewhere else. And then they stop existing there and start existing somewhere else. And that's how electrons actually behave. Sometimes we also combine this with the quantum mechanical model, which is on these same lines, but the idea being the whole universe is saturated with an electromagnetic force field, and electrons are manifestations or excitements in that force field existing as waveforms. We'll talk more about that in chapter 5. Mechanical model. And we use both of these. Both of these two I would consider modern. We still, as I said, we still do use the Bohr model because it's very convenient. It's a nice way to draw things. But the quantum mechanical model and the modern probability electron cloud model are really the way we think about the atom nowadays. Now, the math we do in this chapter, and I'm going to go through this really quite briefly, one for the sake of time and two because you should already remember it, but there's this idea of isotopes and ions. Isotopes are atoms. Well, you tell me. It was a vocab word. Isotopes are atoms. I give you a sentence frame. Isotopes are atoms what?
Isotopes are atoms too.
Same number of protons, but different number.
Yeah, atoms with the same number of protons, but different number of neutrons. And ions is not a vocab word? Probably not until chapter 7. But these are atoms with the same number of protons, but differing number of electrons. And what we do with those is that, and you'll remember this from physical science, and this is what your worksheet is about, so we're going to get quite a bit more practice with this. But what we do with those is we get a given something like, for instance, let's say silicon 30. Well, this is the name, and this is does anyone remember, what's the 30 represent? The mass, yeah, very good, Kendall, the mass number. So from this we can tell how many protons, neutrons, and electrons it has. How many protons must it have because it's silicon? I'm asking you to do this because you've already done it before. Nope.
Well, silicon.
Silicon is right here. Oh, sorry, silicon's right here. 14. It must have 14. You just know that instantly. You just happened to guess a number between 1 and 100 and guess it right. No, how did he know that? That's what makes it silicon. Silicon must have 14 protons. Every atom with 14 protons is silicon, and every silicon atom has 14 protons. How many neutrons?
Would be 14.
No.
30.
No.
It would be 7 or it'd be 16.
It's 16. Gabe guessed and he got it? No. Why?
Because
What's the relationship between these?
If you subtract 30 from 14, you get 16 because 30 is the mass number.
What two things?
Is 1.
Gabe is right. What two things have mass in the nucleus? I'm sorry, in the atom. The proton and the neutron. So these two together must add up to this, the mass number. How many electrons in silicon 30? Now, Whitley, now is your chance. Now there's 14. And we know that because this is a neutral atom of silicon. If it wasn't, it would tell us. And so it must have the same as the number of protons. Now, what about this one? Let's do calcium 40 plus 2. Oh! It's not only an isotope. First of all, every atom is an isotope. But it's also an ion. Now it has a different number of electrons, true. So let's do it. Protons. How many protons? 20. How'd you know? Everyone got it. How'd you know?
Atomic number.
Every atom with 20 protons is calcium. Every calcium atom has 20 protons. Neutrons. How many neutrons must this have? 20. Because these have to be the same? No. Because
40 minus 20 is 20.
20 plus 20 is 40. Electrons, though. Oh, be careful. No.
18.
No, if it's neutral, it would be 20, but it's plus 2. So we must have
18.
2 fewer electrons. That's right. We can't change. Why can we not change how many protons there are? Why can't we say it has 22 protons? That would be plus 2.
Because then it would be.
Then it would be titanium. It wouldn't be calcium anymore. So, right, why do we subtract 2 electrons?
Because electrons have a negative charge.
Say it to the mic. Say it to the mic, ASMR.
You subtract the electrons because they have a negative charge.
Because electrons have a negative charge, and so if we have a positive charge on the ion, there must be fewer electrons. So we know there must be 2 fewer, so there are 18. I think you can do these. There's just one other example I'm going to give you just so we get the other notation right. Let's say we have uranium-238. Well, protons, neutrons, and electrons. This is the other format. This is called isotope format. How many protons must it have? What's the U stand for? Uranium. How many protons must it have? On the bottom.
Uranium 92.
92. It's the number of protons. It's also the atomic number. Neutrons? Math.
Okay. 146.
146. These two added together must equal that. Electrons? 92. Nice job.
How do we get electrons?
It's the same as the number of protons unless it's an ion. And if it's an ion, we have to change depending on the charge. Other questions? Thank you for your question.
Charge, you subtract it.
Yeah, you can remember it that way. What I prefer to remember is that electrons have a negative charge. And so we adjust the number of electrons based on the charge.
Full book of notes.
That's a full book of notes. Does anyone else have any questions? There are going to be on the test and on your worksheet questions about nuclear radiation too, which we just do not have time to talk about. But do you have questions about what we did talk about? We'll talk about nuclear radiation next time. Bye.